idea for a modification of a wheelchair back in January. And they are Mr. Matt Dill, a graduate of Princeton High School in Princeton, Indiana. Mr. Logan Johnson, a graduate of Davis County High School in Davis County, Kentucky. Mr. Marky Laura, a graduate of Francis Joseph Wright's Memorial High School on the east side of Evansville. And finally, Mr. Zach Wiggin, a graduate of Francis Joseph Wright's High School on the west side of Evansville. Gentlemen, please.
Thank you, Dr. Kissel, for the introduction. Welcome, everybody. As Dr. Kissel mentioned, this is our senior design team. I'm Matt Dill. To my right is Logan Johnson, Marco Laura, and Zachary Wiggin, and this is Redefining Mobility via Lever-Operated Wheelchair. So to start, we wanted to show the strenuous movement that it requires to use a standard hand brim wheelchair. In the video on the right, you can see that it's difficult for me to do with the awkward wrist angle, and this causes problems all the way up to the arm, leading from the wrist up to the elbow and then to the shoulder. And from our research, you can see that wrist injuries occur in 53% of users who use a hand brim wheelchair, along with shoulder injuries accounting for 45% of users getting that injury, along with elbow injuries with 10.5% of users getting this injury. And this data was found from the American Journal of Physical Medicine and Rehabilitation. So on the video on the right, it's a little sneak peek of our final design. As you can see on the table, it's Marky using the system, which is lever operated, and through our research we found that a lever operated wheelchair alleviates upper body strain. This in turn can increase the life of the user for the wheelchair so they can use it longer since it's not as strenuous on the body, along with increased terrain travel capabilities. This is due because of the torque output that we have on our drivetrain that we'll be able to get to in a second. So you may be asking, why modular? Through our research we saw that there aren't many wheelchairs that you can disassemble. All of them are one complete unit that can't be taken apart. This is a problem with if something breaks, you might have to order a complete new system. But we wanted to show you a quick sneak peek of all of our modular attachments. Again, we will get into that in just a second. But the reason for this was because of the replacement of the attachments, as I mentioned. Transportability, it is bulky, so it's hard to fit into a standard car. We counteracted that with modular attachments, so you can just take it apart and take it wherever you need to. So our first literature review is from MIT. They made the Leverage Freedom wheelchair. In this design, they utilized a lever drive system, as we have as well, along with a freewheel, which we will talk about soon. The main innovation that I wanted to get to was the multiple test trials done. They had several designs made for different low-income countries, such as Africa and India, and this is due for the terrain travel capabilities. They wanted to get some variability in the design. Our second literature review comes from Calvin University. This is sort of where the modular attachment idea came from. Their lever arms do come off of the system, but highlighted in blue is their frame. That's a completely new frame that they made along with the axle. This makes the system not completely modular, so if something were to break, you may have to order a new system entirely.
For this project, our objective statement is design and develop a series of modular attachments for a standard wheelchair to enhance functionality, enhance user comfortability, and accessibility to new trends. Our list of deliverables is a modular attachment for a standard wheelchair. We have a lever drive system, lever arms, braking system, gear system, anti-tip rear casters, and senior design report, senior design presentation, senior design poster. And as you can see, here's our final design of our wheelchair, and you can see our modular attachment attached. Here's our front view, and here's our back view with the anti-tip rear casters. So our list of requirements: the modular attachments for our standard wheelchair shall not exceed 40 pounds, shall allow the system to be operable under a max of 300 pounds, require no more than 2 people for installation, allow a transversal of a max of 25 degrees, not exceed project budget of $500, not prevent the base wheelchair from conforming to any and all Americans with Disability Act of 1990 standards. So what this means, so the minimum door width is 32 inches, and also the slope grade that a standard wheelchair needs to go up to is 10 to 15 degrees. So we have three subsystems that we have. It's a lever drive system, anti-rear casters, and capital brakes. So going into our lever drive system of our requirements, so shall be installable under 15 minutes, shall allow up to speeds to 1 meter per second for average user. Approximately 1 meter per second is the walking speed, shall offer a mechanical advantage up to 2-to-1 ratio. Anti-tip casters shall support a full weight of the system if needed, shall allow the user to travel up a minimum slope of 25 degrees without tipping. Capital brakes. The capital brake shall stop within 10 feet at speeds of 5 miles per hour or less, shall provide a required force to stop users of all masses within operable range. Brake lines shall not interfere with the lever drive operation.
Alright, so as the boys have already started to describe, the entire intention is having a set of modular attachments. We don't want a standalone system that's already built and put together. We want something that we can utilize. They can use single components, the entire system where they like. What we've done, we've shown here is all the attachments laid out. Starting left, right, you can see our brakes and our calipers, as well as our front gear brackets, our lever arms, our axle, and our rear tips, which we'll describe all of those here to you. Starting off, our first issue to tackle was the wheels themselves. Standard hand-rim wheels that we had on our wheelchair were 24 inches. They do fairly well over most terrains, most issues that they're tackling. However, they still have that awkward wrist angle. So we wanted to find something that not only combined with the system easily, but would have good coefficients of friction for different terrains, since we want the user to be able to tackle different areas. So we just looked into bike wheels. Bike wheels have a lot of testing on their coefficients of friction, and they also have comparable sizes. We did have to go a little bit smaller, unfortunately, which we were able to flip the brackets over so that it matches up. We did calculate that into our torque ratios when we did our final calculations, but it combined easily with our free wheel that we used on the system. Our largest component of the whole project was definitely the lever drive system itself. We worked through each component. Comprised of it was the axle and sleeves themselves, free wheel, front gear bracket, our chain, our lever arms, and then our sprocket itself. It is important to point out, I know it's a little difficult to see in the image, but we did have to 3D print an axle collar sleeve. As it turns around here, you can see that's a white component on the back of the front gear bracket, that image to the right. That holds the axle in place, and we had to run through that in our engineering design. Starting with the front gear bracket, it's located towards the front of the wheelchair, as you can see in the image and on our actual project design. It's used to hold the axle in place, and we did have the foresight to cut some channel cuts into that for weight reduction, as we had designed it a little bit bulky. We started with an initial design that actually had a fully locked axle. It would be thread locked in and in, and we were going to use a small bearing for the connection of the sprocket. However, when we ran through some finite element analysis, we realized that there were higher stresses than we wanted on the axle. We also saw that there was a poor connection between the sprocket and the bearing itself, so we went back to the drawing board and thought what we could do to change it. Well, here we came to our final design. Instead of using a small bearing, we decided to opt out for an oil-impregnated bushing. This is used to hold the axle in place, and as it moves, it releases more oil to the system, makes it a little bit easier to use in the long run. It's also able to be, or the axle is removable, so if there's any damage to the system, anything needs to be replaced, it's easier to pop out than having a welded connection. For our sprocket and chain, the image on the left shows you that we use a welded plate. Like I've already mentioned, this gives the user the option if they wanted to change it out for a larger gear ratio, if any of the teeth damage, anything like that, they're able to replace and swap. We use standard bike chain, that way it was already integrated to the system, it was easy to manufacture. Our lever arms, the entire concept of the lever arms is that with their extended length, as you move your hands up and down, you can change your ratio between the torque to the angular velocity into the system. If you need to go a little bit faster, you can drop your hands down. If you need a little bit more torque for a higher slope, different terrain, you can bring those hands up. We've gone through, and as Matt had mentioned, the reverse stroke on the lever arms does not equal reverse motion thanks to the free wheel itself. The way it's designed with a ratchet and pulse system, as you bring those lever arms back, it doesn't engage the wheel itself into reverse motion. We'd originally intended to do a bended angle on those lever arms, the idea being that it'd be more close to a standard bench press position some of you might be familiar with. However, we were concerned with additional stresses due to bending being introduced, as this thing will see a lot of impacts out in the real world. It's going to see continued everyday use. We wanted to eliminate any stresses that we could. This led us into our final design for the lever arms. We opted for just a straight, full-length lever arm. As you can see in that far image on the right, we actually designed and developed a small end cap pin that's welded into the lever arms and uses a threaded bolt cap. Benefit of it being easy to remove, it's easy to change out. The user can take that off quickly if they need to and place that back in. And it also makes it well for being able to get the base wheelchair through doorways should it be a smaller size.
So just to reiterate things that Logan talked about, this is the final design of our drivetrain. Starting on this GIF, you can see the grip at the top. This was just made for comfortability for the user. Also, leading down from that, you can see it's bolted connection to the axle, which then holds the sprocket gear with the freewheel and the chain, keeping those together so you get torque ratios and whatnot. And this is connected to the front back bracket. And the axle sleeve, you can see it's still a little difficult to see on there. We do have a backup slide for that if you do want to see it. But that was because whenever we were testing the system, the axle wanted to come out of place a little bit because of vibrations and things like that. So we 3D printed this design just to fit on snug so it doesn't come loose. And the picture to the far right is this implemented into the system. With this being our largest portion of the project, we really wanted to focus on making sure that the user was safe using it and wouldn't fail during testing or if they were using it in everyday use. So what this shows is if there was a full axle lockup, this would be if someone's on a gravel terrain and maybe a rocket gets stuck in between the axle and the bushing. So what this shows is the user outputting a force on the lever arms, which are made out of 6061 T6 aluminum. And this has a yield strength of 40,000 PSI. And from this test, we can see we have a theoretical factor of safety of 1.55, showing that the system will not fail during this occurrence, if it does happen. With the drivetrain being set in stone, we were comfortable with that. We can move on to the anti-tip casters, which is another modular attachment that we wanted to provide for safety to the user. This image on the left shows this with the bolt connection in the sleeves that were originally made for armrest. Leading to the picture on the right, the caster wheel has a steel housing on it, and we wanted to implement that, so we had to make an end cap similar to the lever arms for the aluminum tubing. Go ahead. And you can see it's bolted. The caster wheel does come off, so that's how we were able to make that connection. And the image on the left shows the casters being implemented into the system. This also leads to another issue. If someone were to fully tip over, there's an initial tip that happens to the rear casters, and then what we wanted to test was if the full weight of the system was put onto the rear caster wheels, if it would fail. So this shows that the wheelchair is approximately 52 pounds, so we put a 352-pound force onto the caster wheels to see if it would fail in the action of full tipping, and we have theoretical factor of safety 2.5, so the user will be good with that.
So after what Logan and Matt described about the lever drive system, how the wheelchair moves forward, how are we going to stop the wheelchair? Not only are we implementing bicycle wheels into the project, why not implement the caliper brakes shown in the image? And then another question occurred to us is, how are we going to mount the caliper brakes onto the Quickie 2 wheelchair? So this is our first preliminary design. Our idea was to mount the brake mount on to the front gear bracket, but due to us communicating, we decided to relocate the brake mount somewhere else. And we decided to relocate the brake mount at the rear of the frame above the wheel. As what I just said, this is the location where we changed the brake mount. So there's two connections. There's a bolt connection and the caliper brake connections. So the idea was to have these brake mounts just already there, and then our issues that we occurred was excessive vibration, and the brake mount weren't stable. So this comes to our final design of our brake mount. As you can see in the image on the right, and there's a video showing of us having a 2-bolt connection and a pin connection. So the pin connection gives us better alignment, and also the bolt connections give us a better structure on the frame. And as you can see, the center of the bolt is aligned with the thread, and this gives us better alignment, and this brake mount gives us reduces vibration.
All right, here's a little time lapse for you guys. This is us assembling all the modular attachments onto the wheelchair. Our primary focus of doing this was to find if our time assembling all these attachments on the wheelchair would be our requirement. Another thing that we were trying to find was what would be the hardest attachment to put on the wheelchair for the user. What we quickly figured out was tensioning the chain was actually quite difficult. You have to pull back on that bicycle wheel and then tighten the wheel onto the frame. So in future design iterations, we want to make sure that is a lot easier on the user. And as you can see, we completed in about 14 minutes with a few practice attempts, so that falls within our requirements. This is us disassembling the wheelchair. As you can imagine, a lot of these attachments are just additions. You're not really replacing a whole lot, so the disassembly process is a lot quicker. So the only thing we're really replacing when we're disassembling it is the bicycle wheels back to the hand rim wheels. And as you can see, that was completed in 11 minutes, which is well within our required time. Once again, here's our final design. Just to recap, we have all of our attachments on there, the drivetrain system, the lever arms, the brakes, the anti-tip casters, the brake mounts. Let's go through our requirements that we met. So through our testing, we figured that the modular attachments of the wheelchair shall not exceed 40 pounds, allow the system to be operable under a max load of 300 pounds, require no more than 2 people for installation, allow traversal of a maximum slope of 25 degrees. Through our testing, we were able to verify all those. And then not exceed a project budget of $500. Unfortunately, we did go over that. One concern that was overlooked when we were developing this wheelchair was for our left-hand side bicycle wheel, it has a left-hand side freewheel, which means it has to be replaced with a left-hand hub and a left-hand freewheel. So that had to be taken into a bike shop, which unfortunately cost us about $200, which put us over budget. And then not prevent the base wheelchair from conforming to any and all Americans with Disability Act of 1990 standards. We did conform to that. For our subsystems, the lever drive system shall be installable in under 15 minutes, shall allow speeds of up to 1 meters per second for average user, shall offer a mechanical advantage of up to 2 to 1. Through our testing, we were able to verify all those. Anti-tip casters shall support the full weight of the system if needed, shall allow a user to travel up a minimum slope of 25 degrees without tipping. Also, through our testing, we were able to verify those. For our caliper brakes, shall stop within 10 feet at speeds of 5 miles per hour or less, shall provide required force to stop users of all masses within an operable range. Brake lines shall not interfere with lever drive operation. And again, through our testing, we were able to verify those. So some of our lessons that we learned. On the left-hand side, you can see some bolts that have failed on us. Those were originally used for our lever arms, that bolt connection. And quickly after installing those, after a few uses, those did fail due to bending. Since then, we have upgraded to a grade 5 steel bolt, which has not failed us yet. On the right-hand side, you can just see some of the problems that come with learning new equipment at the AEC. That there is a tap that was sheared off into one of our caps. So, more time, it slows down our production process, but, we've also learned from it, so now we know for next time. Some of our contributors, this project couldn't have been possible without the AEC, the Electrical Engineering Lab, Optics Lab, Computer Lab. Jennifer Wright, she's the one who provided us with the wheelchair, so we really appreciate that. Donna Ewert gave us extra funding for the project, and Jamie Curry. We'd also like to give a special thanks to Dr. Kissel, Dr. Cuban, and Justin Amos for their assistance throughout this project. So some accomplishments. We now have a better understanding of forces and stresses and bolted connections, increased knowledge in design iteration process, importance of collaboration and communication between engineer and manufacturer. Throughout this whole process, we spent a lot of long hours in the AEC. Sometimes we get on each other's nerves, but we worked through it. It was a really big team building exercise, but I think in the end, we were really proud of what we did. So appreciate you all coming, and now we are open for questions.
No, just you first.
Okay. Could you talk about the loading condition on the anti-tip casters?
Yeah. Are we referring to that finite element analysis?
Yeah.
Okay.
Yeah, specifically for the back tipping casters.
Yeah, so as I was talking about through the slides, the anti-tip caster is there for the safety of the user. So if they were to go up a slope that wasn't approved, like that max 25-degree slope that we're talking about, if they were to tip completely onto that, which means that the full weight of the user and the wheelchair was on it, then the caster wheels would have to support that full weight with the aluminum that is on there. And through our testing, we found that. We also tested this, but with the tip angle, it does slide before you get to that angle. But through our testing, if that were to occur, if someone had a higher coefficient of friction, if they were to somehow manage that, the casters would hold for eventually tipping completely over.
Okay. Where were your load forces applied? Like what directions?
So we've taken them off of there just for easy picture, but as you can see on the actual final project, the wheelchair itself has pre-made sleeves that the armrest would normally sit in. We took those out and used those to place our rear anti-tip casters into those. So we treated forces as that being a closed connection right there around where that sleeve is, measured all that out, and then we did forces running down the length of the caster bars, assuming that it's fully tipped, so it's placed down through it.
Okay.
So that also, if it were to bend the top angle, come through that sleeve, anything like that, any failures that we could have.
So basically, like, as it's sitting here, you have a horizontal force going at the top end of the caster where it attaches to the wheelchair, and then a bottom force acting as the ground. So you basically have a force going this way.
So basically pushing through it. Trying to treat the system as if it were to fail. Is that going to compress on itself? Is it going to bend through?
Okay.
That way it doesn't snap off or have any shear.
Sweet. Awesome.
Go do.
Did y'all look into any standards or safety measures for guarding the chains and the rotating sprockets and stuff?
That's a
as
great
far
question.
as
Great question.
pinch points and stuff?
Yeah. So one of our original main intentions to include in this project was actually a gear housing cover. It was designed kind of like an airplane fuselage, a little bit aerodynamic. The only issue with this is we talked to Dr. Klobowski, it was pretty darn big, so we didn't have any printers on campus that would be able to fit that. He had discussed with us that we could maybe make that into 2 components and have some fin connections, but we were worried with impacts and vibrations and the PLA, that was going to hold up. We didn't feel it was right to kind of waste the university's money if we didn't think it holds in the first place. But future iterations, we would love to have something maybe injection molded and designed out. That way the user is protected from any interaction with the chain, and it keeps debris from blocking up into it. Any other questions?
Was there any consideration for the angle that the chair sits at with the increased leverage? You know, Marky pulled a wheelie in
A
his
little bit,
video.
So definitely was thought about and put into it. We ran through some of the calculations, looked into it. It's pretty complex on the different user sizes, different user loading, someone who's an amputee in the legs, where their weight distribution is, everything like that. That was the intention with the rear casters of, we did multiple test trials. If someone really tried to get after it and put some force into it, those rear anti-tip casters will catch you before you have any full tips. Absolutely.
One of the big driving forces of this project was to reduce strain on body parts. So by moving and transitioning your wrist from a position where they're moving the wheels to a position where you're now grabbing these posts, do you feel like the design has reduced impact on the wrist joints?
Absolutely. We do actually have in one of our backup slides here some research that we had done, different literature reviews specifically for that topic.
Okay.
Directly discussing the more neutral wrist angle of a lever drive system versus that awkward flexure that you get in a hand rim.
Okay.
It also discusses the stroke pattern as far as peak power outputs through the upper body muscles versus focusing on just the lower ligaments and joints of the wrist and elbow.
Thank you.
I think Dr. Logrossi had a question. Going off of what Dr. Grabowski was asking, what is the effect on the shoulders then?
So that was in one of the literature reviews. So with it transferring the muscles up to the top, it was a concern in some of the reports that we had read as far as extended use. Usually your shoulder's going to give out more than your pectoral will. We don't have a great pit photo in the presentation, but in our report we show that it actually alleviates some of the strains through those upper shoulder muscles, and it focuses more on the pectoral chest, kind of in that chest press motion, than it does any joint issues.
No, please, Brad.
Does the user have any way of backing the chair up now you put the
Great
levers
Okay.
on?
Unfortunately, no. With the free-wheel design, it's only made to go forward. As Logan was talking about with the reverse stroke, it won't move at all because of that free wheel. So that would be a future design iteration that we need.
To build off of his real quick though, if any of you are familiar with a standard hand rim wheelchair, you can grasp one of those wheels and hold it closed and then power the other to do almost like a 0-point turn. That was the intention with the caliper brakes, and we did test and prove that you can hold the brake on one side and you're able to turn in a full 0 turn.
Yeah, if you have room to do that.
Correct. That is something that in future iterations though, that we could look into maybe a gear change that puts it into a reverse system and maybe operate.
Thanks.
No, no, please.
So, did you test it on the slope? Do you have any photo of testing it on the slope or any land?
Absolutely. Here in one of our backup slides, we used up at the AEC one of the grass slopes. We did want to test on grass just in case Marky fell over. We didn't necessarily want to hurt him too bad. But we were able to achieve about 33 degrees before we noticed that it started to slip due to friction. That's most likely caused because the rear casters are much more slick than the actual bike wheels themselves are. We did push it passes with Matt tipping Marky and me holding it so it wouldn't slip to see where we got to. I believe we reached about 39 degrees before Marky felt a little bit unsafe sitting in it. Yes, sir. Go for it.
So, go back to 39, please, slide 39. Actually, it's not a question, it's just a suggestion. I think that the accomplishment also should include or referring to having the end user in mind. You know, during the presentation, you several times talk about preventing this, avoiding this. So I think that, you know, keeping in mind the user, right? The well-being of the user, the safety.
Absolutely.
You know,
That is a key
just
point.
Just a humble suggestion.
It is a key point that we have in our report, and I'd be happy for all you guys to read that once we have it posted for you. We do discuss kind of the project itself as far as the build phase, and then with the end user in mind as far as total cost of what they have to purchase the wheelchair, how it's going to work in their day-to-day life, trying to focus on that more than anything.
Thank you.
Absolutely.
Thank you very much, guys.